about applications of function models. In particular, we're going to be comparing linear models, exponential models, and quadratic models. To do that, we're going to analyze an activity called the bald eagle, starting back from near extinction, where we'll be analyzing the population of bald eagles since 1963. So here's the scenario. It is estimated that in 1963, there were as few as 487 nesting pairs of bald eagles in the lower 48 states. These numbers are low when taking into consideration that when the bald eagle was made the nation's symbol in 1782, the U.S. Fish and Wildlife Services estimated there were as many as 100,000 nesting pairs in this region of the United States. What caused the decline of the eagle? Initially, the cause of the decline was the competition of food with the increase in migration of European settlers. Following World War II, DDT was used commonly as a pesticide to control mosquitoes and other insects. Unintentionally, it was washed into nearby waterways, contaminating the bald eagle's primary food source, fish. After protection of the Endangered Species Act, the bald eagle has made a recovery, leading to a removal from the endangered species list in 2007. The following activity is designed for you to work with a partner to do some internet research and determine a curve of best fit during using the data provided. So we're provided with a table, and it tells us in 1963 there were 487 pairs. In 1974 there were 791 pairs. In 1981 there was 1,188 pairs. In 1984 there were 1,757 pairs, etc., all the way to 2006, where there was 9,787 pairs. 9,789 pairs of number of pairs of bald eagles. So this data is provided by the U.S. Fish and Wildlife Service. So let's start with answering our questions. Why do you suppose the U.S. Fish and Wildlife Service does not have any data after 2006 for the bald eagle? So we know in 2007 the bald eagle was removed from the endangered species list, so we can deduce that the reason that they don't have any data after 2006 is the bald eagle was removed from the endangered species list. Eagle was removed from the endangered species list. Identify the variables, which is the independent variable, which one's the dependent variable. So if we look at our table, we can see that we have years and number of pairs. So our year will be our independent variable, and our number of nesting pairs will be our dependent variable. The independent variable will be the year, and our dependent variable will be our number of nesting pairs. Okay, questions 3 through 5. We are going to use Desmos to create a scatter plot and to figure out whether the graphs are increasing or decreasing, whether it's positive and negative, and what the correlation is, and what function best models this data. So first, let's get our scatter plot. We're on desmos.com right now, and we're going to add an item. We're going to add a table. And we're just going to enter in all the years. So starting with 1963, 1974, 1981, 1984, 1986, 1987, 1988, 1989, 1990, 1991, 1992, 1993, 1994, 1995, 1996, 1997, 1998, 1999, 2000, 2005, and 2006. So we've entered all of our years in our X list. Now we have to enter all of our pairs in our Y list. So we're enter 487, 791, 1188, 1757, 1875, 2238, 2475, 2680, 3035, 3399, 3749, 4015, 4449, 4712, 5094, 5295, 5748, 6404, 6471, 7066, and then 9789. Okay, as you can see, we can't see any of the data in our list. So what we're going to do is we're going to click this magnifying glass and we'll be able to see all the points that we just plotted. Next question reads, by analyzing the graph, does this appear to be an increasing or decreasing function? And does there appear to be a positive, negative, or no correlation? So if we look at our graph in Desmos, it does appear to be increasing, and it does appear to be a positive correlation because the function is increasing. So let's write in our answer. This appears to be an increasing function. With a positive correlation. Because the graph increases as you move from left to right. Okay, determine which function best represents the model of the situation, linear, quadratic, or exponential. So to do that, what we need to do is actually analyze the data. So we're going to be sticking to Desmos for this. So to do that, first let's figure out whether it's linear. So we're going to do y1 tilde mx1 plus b. So using the linear model, we have a r squared value of 0.82, which means 82% of the data fits the model, and then the r value is 90.9061. So it's a strong fit, but you can see it's not a perfect fit. So let's try quadratic. y1 tilde ax1 squared plus bx1 plus c. So we have an r squared value of 9704. We don't see the r value, but we can take a square root of that r value to find the r value. So the square root of 0.9704, and this is a really strong fit. 90 0.9850. So it's considerably better than the linear model. Now let's try the exponential model. So you have y1 tilde a b up to the x1. So again, with the exponential model, we just have an r square value, so we have to do a square root to find the r value. So that'll be just square root of 0.9556, and we have 0.9775, which is slightly lower than the quadratic model, but we're going to go with the exponential model because with the quadratic model, as you can see, it's assumed we know data before 1963 saying that it's decreasing. We don't know when it started decreasing or if it's actually 473 pairs. So the best model we can go with will be the exponential model because it is increasing. So that's the model we will go with. So the exponential model fits data best. And we don't know anything about before 1963. And we want to write down our model. So it's going to be 1.0202 times 10 to the negative 55th. Let's just shrink this down. 0202. And our b value is going to be 1.07002. And that's going to be raised to an x. Number 6, using the table, graph, or function, identify the domain and range. So our domain is easy. That's just the smallest x value or the smallest year. So that would be from 1963, and then we're going to end in 2006. And then our range is going to be from 487 to 9789. So we chose the exponential model, so just to unhighlight the quadratic and the linear model. So we look at the exponential model. Even though not every point hits the curve, a lot of the points are very close to the curve. So we will say this is going to be a strong correlation. We also know that from our R value, which is for the situation 0.9775. So let's answer that question. That's the question 7. Draw a smooth curve, which we did with technology, and this shows a strong correlation. Using the function you found in question 5, determine the approximate bald eagle population in 2015, 2020, 2025, 2030, 2040, and 2050. So 1.0202 times 10 up to negative 55, parentheses 1.07002, and this time we'll raise it up to 2020. So in 2020, we're expecting 24,005 pairs. We skipped 2015, so we'll go back and we'll copy this. Control C, Control V, and we'll change this out for 2020 or 2015. And then same thing, now we want 2025. Shows up 33,672 in 2025. Paste it. Now you want 2030. 47,231. Control V. We want 2040 and 2050. 92,929. And then one more time. 2050. 182,839. So let's just write these down in our notes. So we'll just write them down in order. 19,235. 27. Just wrote that. Let's shrink this. So first we have 17,114. Then we have 24,005. Then we have 33,672. Then we have 47,231. Then we have 92,929. Then we have 182,839. Do you think you can use this function to predict the bald eagle population for several years after 2050? So we actually predicted up to 2050, which by good statistics, we don't have data past 2006. So even much after 2006, that's just too far to go into the future. So now we don't have enough data to go much farther than 2010. So we'll say, no, this is too far past the known data. And using the function you found in question 5, determine when the bald eagle population will hit 100,000 nests in pairs like that of 1782. So to do that, we're going to graph y equals 100,000. So say y equals 100,000. And we can't see it, so we're going to zoom out. And now we can see it, so now we're just going to find the point of intersection. And it looks like in 2041, so between 2041 and 2042, we'll hit the 100,000 nesting pairs. So between 2041 and 2042. Hopefully this helps you have a deeper understanding of how to depict a curve of best fit when given a set of data and answer corresponding questions.